Hello, everyone. Thanks for sticking it out until the very end. I appreciate you all being here. Hopefully, I can keep you all awake. I see people have brought the chips and the popcorn, so yeah, I hope I'm able to keep you entertained and informed. So we have a little bit of a packed agenda today because I have mashed together not one, but two talks together into one. So we're talking both about how we use serverless and how we use ARM and how we use serverless and ARM together to get more efficient results. So today I'm going to tell you about how you might find it useful, how we're using it a little bit unconventionally. We'll talk about some of the pain points because, look, I'm a site reliability engineer. I'm a pessimist. I like to talk about how things break and not just, the ideal conference diagram and, the architecture whiteboard. I'm going to tell you how it actually breaks, what you might want to do if you're going to experiment with this. And then fourth and finally, I'll tell you about how to make it cheaper and more cost-effective and more environmentally sustainable. So first, let's talk about what people use Lambda for. Normally, you think AWS Lambda, you think serverless, you think, OK, API gateway, or maybe something that's consuming off of a data bus, right? Like, you don't necessarily think big data analytics, you're thinking streaming analytics. But in our case at Honeycomb, we use Lambda to optimize our custom data store, which is called Retriever. But me saying the words Retriever doesn't mean anything to you, so let's talk about what you, the actual end user developer, might actually use it for. So we do real-time event aggregation. So we're collecting data from our customers, and we're giving people insights into potentially what's happening with hundreds of millions of events or billions of events that they've sent to us in the past. And they are asking those questions in real time, not necessarily kind of pre-canned things that they've already pre-aggregated or said, I want to measure this in advance. And also, because of the dog puns, so this is my golden retriever mix. Her name is Flurry. So Flurry is a very good dog. So we do real-time event aggregation, specifically over trace data generated with OpenTelemetry. So hi, I'm Liz. I'm the field CTO at Honeycomb, and also I'm an AWS community hero. So if you have any complaints to forward to the AWS team, I can do that as well. And boy, do I have a lot of interesting feedback that I've given to the AWS team over the years. So Honeycomb empowers you to have observability, and this is not a Honeycomb sales pitch. This is literally just me telling you what's our use case, why did we start to use Lambda to experiment with this in the first place. So originally, in the bad old days, there was monitoring, and monitoring was, here are the things that you want to pre-aggregate, you want to count and make super fast, and anything else you had to grep through logs, and it was potentially really slow. So what we see as observability today is helping people get insights into things they didn't anticipate in advance. But ultimately, they're still driving at that same goal of helping you understand your systems and reconcile your mental model of what's going on inside your systems. So I was able to get the live demo working. Good news, because we managed to get my screen mirroring working. So I'm just going to say, hey, show me all of the traces that show me all of the traces where they originate from real users. Query source is normal. And let's group them by tenant ID, right? So this is our dog food data. This is how we observe our production environment. So I can, just as fast as it takes me to literally pick up my cup of water and get a drink, I can see who are the most popular, who are querying us the most times, and how many concurrent queries are they running at a time. And it's reasonably fast, right? Like faster than I can take a sip of water. So if speed is the goal, how do we actually achieve that as the volumes of data increase? So that's what this is about. It's about fast queries across any combination of fields, but this is not just a pain point in observability. You can imagine that if you have a data lake, if you have a BI use case, that this may be useful to you, because it turns out that data analysts also are very expensive people who you want to keep happy and you want to enable to give better business outcomes so you don't accidentally order 1,000 of the wrong widget or something. So architecturally, again, this is OpenTelemetry, and then it goes into a columnar store. But the challenge is how do you actually scale out the columnar store? Because eventually, it exceeds the capacity of one machine. So speed, 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 because user experience, and if you disrupt the user's flow, if it sits there spinning so long that you're like, actually, I'm going to make a new cup of coffee, or I'm not going to wait for this to finish, then it becomes unacceptable. So the way that we've initially handled this is to decouple the stateful and stateless parts of our system so that we can scale them independently. because things that need to scale based off of the amount of incoming data are very different than things that need to scale based off of when someone hits the run query button. So what if we separated those things and enabled data ingest to be stateless, and then we funneled all of the stateful stuff through Kafka and then reading off of the Kafka topic? So, but at the end of the Kafka topic, right, like there has to be something stateful storing the data. I can't just write it to dev null, right? So we have the retriever system that basically takes in the data and it serializes it to NVMe solid state storage. Fun fact, originally, the system that inspired retriever was called Scuba, and it was a system developed at Facebook, now Meta, and that system stored the data entirely in memory. You can imagine that that gets really, really expensive, and you probably only can really do it if you're Meta. So our initial thought as to how we can make this better is, why don't we just store the data on NVMe, because NVMe is a lot less expensive than RAM. But it turns out that NVMe storage has a finite capacity. So we'd initially, say, OK, let's just scale out horizontally, right? Like, we can, maybe we can't expand the size of NVMe on each worker, but maybe we can have one worker act as the aggregation layer, and then to farm it out to other parallel workers that are also storing the data, and that way we can scale out to the size of the NVMe drives. And what data are we writing? What is the format? Well, the essential kind of optimization here is you only want to read data that you absolutely have to. So if a query doesn't call for the field, for instance, like user agent, if I didn't query user agent in that query that I just ran, then I shouldn't be touching the data relating to user agents, right? And also that the data that's stored for each individual field is likely highly repetitive, right? For instance, my timestamp field is probably pretty incrementing. For instance, the HTTP status code is usually one of either 200, 500, 400, right? Like there are only a finite number of those status codes. So that enables us to get pretty good compression, because at the end of the day, the smaller the amount of data that you're scanning, the faster it is. And then the other piece that we do, that again Scuba also did, is we think about the timestamps that are relevant, right? If I'm only querying the most recent 2 hours of data, I don't need to scan data that was generated 30 days ago that couldn't possibly have any relation to my query today. And I might want to scan this, the segment of data that was created an hour and a half ago that covers from an hour and a half ago to 2.5 hours ago. But data that is too old and couldn't possibly apply to my window, don't even bother reading it. So that's how we initially tried to make it super fast, right? Like, just working with the constraints of a server-full application that was storing data on local SSD. And that got us a little bit far, but more and more data came in, and eventually we started having to act more like a ring buffer, right? Where you are storing the data until your disk fills up, and then you discard the oldest data, and then suddenly you look at your data store and you're like, wait a second, I'm aging out data that's only 50 minutes old. How many of you have needed to debug a problem that was more than 50 minutes ago, right? So this wasn't fit for purpose. So instead, we said, OK, what if we tiered the data onto AWS S3 or to object storage, right? Like these are just files. Object storage exists for a reason. We can just write it, and then we can get it back whenever we need it. And we'll have infinite storage, and it's going to be great, because now customers can query for months if they need to. Yay. But it turns out there's a minor problem with that, which is, sure, querying from your local NVMe SSD is reasonably fast and also has some reasonable proportion of data to the number of CPUs. But what happens when you're now having to fetch back millions of files from S3, and you're having to grovel through them with 4 CPUs or 16 CPUs? The amount of time that it took started becoming linear, or even in the worst case, super linear. Not great. So at this point, we're violating the promise of running a query should be as fast as taking a sip of water. The core problem here, and why we had to move to serverless, was it actually starts mirroring some of the data, some of the use cases that you think about when you think about serverless computing, right? Like when you have something that happens on demand, right? You only want to use the computing resources when you're actually doing work. And when you're not actually doing work, then you want to go ahead and hand them off to someone else to use, right? Make them Amazon's problem to deal with all of that compute that you're not using. So it's a lot like my dog, right? Like she loves to play with her toys. She'll get them all out over the floor, but like someone has to pick them up and put them back in the bin, right? Like I can't just leave the dog toys lying on the floor all the time. So this is where Lambda comes in, because Lambda works really, really well with S3. Because S3 is really horizontally infinitely scalable object storage. And you know that you're going to essentially need to map reduce, right? Like you're going to need to read those files off of S3, and that you can parallel compute them. This is an embarrassingly parallel problem. So by saying, OK, each retriever now can call out to a set of lambdas, and each lambda has, in turn, its own work list of these are the files, the segments I'm reading off of S3, then we're able to kind of merge this together in a 3-tier merging architecture to get users' results quickly. So now, no matter whether you're querying 1 million files or 100,000 files, it still takes less than 10 seconds to do. This is great. And even better, we get perfect utilization, right? We're buying the compute in 1 millisecond units. So this is kind of how we were able to scale up our data store from, we originally had something like, 80 gigabyte machines and 80 gigabyte SSDs, and we had, I don't know, maybe 30 of them. And now we're managing over a terabyte of storage. And yeah, so we've grown over 20 times in 5 years, and we mostly haven't had to worry about provisioning, capacity planning for the query workload. But the consideration is, I said that this workload is similar to, you rock up to the serverless brew page and you scan and you order a coffee, right? But this is not just one person ordering one coffee and triggering one serverless function to run. Because when we ask to run a function, now we're asking actually for tens of thousands of concurrency, and we're asking for 4 vCPU each. So we're actually setting 100,000 CPUs working at the click of someone pressing a button. And Lambda normally doesn't let you do this. Normally there is a burst limit, and if you try to run more queries than your burst limit, you get a HTTP 429, which tells you chill out, slow down. And eventually, if you keep on pushing your concurrency limit, AWS will raise your concurrency limit. But it originally required 1 minute of sustained load, but now it requires 10 seconds. But even 10 seconds is a little bit too slow for us, because by the time that we run those 10 seconds, ideally, you already have your response back. We're not trying to retry and retry and retry. So under normal circumstances, we would never hit that situation where AWS automatically bumps our concurrency limit. So that is the only case where we've had to talk to AWS and said, let's go ahead and capacity plan, and you tell us how much spare compute you have lying around that you can lend us, and we're willing to wait if it's not available, but if it is available, please just go ahead and give us all tens of thousands of concurrency. So by negotiating with AWS team, by kind of managing the trade-offs of queuing, latency, and concurrency, we're able to achieve this level of high performance. So make sure that you are retrying, but with a backoff. Make sure that you are measuring what the performance is that you're getting, and communicate with your account reps, because they're the people, and the service team are the people who can actually enable you to get that level of scale, if that is something that you are doing on purpose and is not someone accidentally triggering a Lambda to S3 bucket notification to Lambda to S3 bucket notification infinite loop. So they know that to expect this workload from us. Secondly, let's talk about cold starts. So ideally, we want to respond within 10 seconds. And also, we're running across many, many workers, but sometimes the Lambda is invoked against a backend worker that does not have our runtime loaded. So how do we manage this? Well, again, we measure it, and it looks like in practice, our experience has been, it takes a small number of milliseconds to actually send our zipped Go binary to the machine. But our zipped Go binary is less than 30 megabytes, so it's not that huge compared to a container image, which I understand Lambda does support now, is sending Docker container images. So thank goodness we don't send container images, because time is critical here. And then our startup time is about 15 milliseconds to 50 milliseconds, and then we actually start working. And then the worker goes to sleep, which is kind of cool. You can actually watch them go to sleep and then eventually get garbage collected if no one runs a query for a while. But there's another bit here, which is when you're running millions of invocations, some of them are not going to return. Not within 2.5 seconds, not ever, until the Lambda SDK gives you a 30-second timeout. So what do you do in that situation? Because customers are not going to be happy if you said, hey, by the way, there were no users that were accessed by this attacker. Except for you're like, actually, whoops, I forgot to scan the 0.1% of data that did have the data points that said the user's data was accessed, right? So what we do is we do impatience. We retry the slowest 1% of requests, both to guarantee completeness of data and also to make sure that we're providing a satisfactory user experience. Because one of the cool things about a system that's as distributed and as scaled as Lambda and S3, if you retry a request that failed, 99.9999% of the time, that retried request will succeed, even though it's the exact same payload the exact same files that it's trying to access. It's just sometimes your request gets eaten by the distributed system. You are a part of the distributed system, and we just use the patterns for distributed fault tolerance to work around that. So if you just impatiently retry the slowest 1% of requests, it gives you some reasonable bounds on how quickly your requests are going to come back. There's another problem here. Funnily enough, there's a gentleman here from AWS that was picking my brain about this. So again, Amazon Lambda is designed with, you have to back it with a API gateway, or you have to back it with SNS or something like that. They're really not happy with this idea of sending arbitrary gRPC or protobuf encoded payloads. So we're actually straying in the limits of, we'll send in a single payload, hey, by the way, here's 2 megabytes of data that contains a list of files to read, a query specification. But we have to encode it from efficient protobuf format, which we internally store it as, to JSON to serialize it over the wire and compressed. And eventually we wound up serializing the payload and just base64 encoding it and putting it in a JSON file that says compressed _ payload : AAAAA something something. The other thing is the return values, right? The return values inline in Lambda, you can only get up to 6 megabytes back. If you're potentially running a high cardinality group by, if you have potentially hundreds of thousands of returned group fields that you're saying, hey, there were 5 of this particular user and 3 of this particular user in this batch, and you have to aggregate and merge them back together, the results can be larger than 6 megs. So you have to wind up creating files on S3 to kind of act as that message bus between temporarily park your data rather than have it returned in line. But again, why is this worth it? It's speed. Nothing else would possibly let us invoke millions of invocations to have it come back within 10 seconds and achieve perfect utilization. And sure, you might say, but Liz, Lambda is so expensive. Well, kind of. Have you ever had an EC2 box that you've had to pay for while it was booting up, and then while it was idle, and then while you were deciding whether or not to shut it down because of utilization? We don't have to worry about that. So yes, Lambda is about 4 times as expensive as running EC2 flat out per core. But gosh, if I can have 100% utilization, that more than makes up for it. In order for Lambda to be more expensive than EC2, given that we get less than 5% total utilization, it would have to be 20 times more expensive for it to be worth it for us to run EC2 VMs flat out for this. And yes, we do measure the cost. Yes, we have service level objectives set on, this is the list of customers we expect to cost a lot. And if there are any other use cases where people are running a lot of queries and hitting cold storage, we want to know so that we can optimize it, because otherwise, yes, the cost will kind of run away there. So the trade-off that we are making here is that we think that human attention is very important, and that it's worth spending money to optimize around returning results fast for arbitrary queries rather than pre-aggregating or rather than waiting for something to come back. But it turns out that maybe for queries that are predictable, right, like where someone has some kind of report that they run every night at 2 a.m. and that a machine is looking at, maybe we shouldn't be running this against Lambda. But at the end of the day, we would still pay the cost of the S3 accesses. We would still pay some of these fixed costs, even if we weren't paying for Lambda. But what if we could make all of this a lot cheaper? What if we could make it 30% cheaper? Wouldn't that be nice, right? Like slashing 30% off of a hundreds of thousands of dollars per month bill. That sounds awesome, right? So I agree, and I think it's not just about the money. I think that it is the socially responsible thing to do to use lower power consuming compute. And yes, Amazon does pass the savings on. So in Australia, where I spent a good portion of the year, 2018 and 2019 were some of the worst years on record for climate change. In particular, there were some of the worst bushfires we have ever seen in Australia that happened in the 2019 fire season. So what you're looking at there, that's the map of temperature anomalies. And this one's the rainfall anomaly. This one's the temperature anomaly. But you can see it was a hot, dry summer. And things were burning. At Yao 2019, you could smell the smoke in the air. Your eyes would water when you were walking through the streets of downtown Sydney. It was not a good time. And why is this happening? And it's not just too little rainfall, it's also too much rainfall at the same time. Why is this happening? Human-generated climate change. And software is a significant portion of this. So I learned, I think similar to many of you, that in 1999, 25 years ago, that's both when this conference was founded and also when the word carbon footprint was founded. And do you know who created the word carbon footprint? Fossil fuel companies, because they want you to believe that it's your individual responsibility. Guess what? People don't have carbon footprints. Companies do. Companies are responsible for a majority of those emissions. And yes, at this point, carbon emissions from computing are just as high as carbon emissions from aviation. So if you think about flight shaming someone, next time think about, how many servers did I set running? How much does that cost the environment? Right? It's not just a number on your AWS bill. It's actually something that you have a much more meaningful opportunity to affect as a technologist, the resources that you use compared to the amount that you fly. So offsetting is not the answer, because offsetting, it's just bullshit. People just make it up. If people can find a way to cheat the system, they will. So wasting less power is, and that's why I strongly feel that Graviton and ARM chips are a key component of how we make it much less expensive to our wallets and to the environment to do the things that we're used to doing with computing. So how to use less power? Don't run the workload at all. In particular, does it really make sense to use an AI model for that, or would you be better writing a shell script? Optimize your workload, profile it, set performance measures on whether or not you're regressing if you're doing something that's going to spend a lot of cycles. We certainly do that. And then finally, use the most efficient possible technology that you can. So we've seen really great results with Graviton, and I want to share what was that migration like, both in terms of migrating our server full and our serverless workloads. Our serverless workloads were some of the earlier workloads to migrate, but not the very first. So just to recap, and I don't have to talk about a lot of details of this because Matt covered a lot of it in his talk. But in short, architecture basically relates to the assembly instructions that your computer is executing, how those get translated into what the transistors are actually doing on the silicon. And essentially, you can think of the architecture as an API for you as a programmer to interact with the hardware that's running. So originally, there was a plethora of different architectures, and everyone had to pay attention to, does my software run on a VEX or on a Z80 or on an S370? But the era of desktop computing came along, and it seemed like it was just going to be x86 or Macintosh. And then after the world went to 64-bit, suddenly it was like, OK, actually, Apple has moved entirely to x86 64 processors. PCs are using x86 64 processors. The architecture wars are won, right? But that's not entirely accurate, because silently what was happening, oh man, I left my prop back there, my cell phone. Don't worry about it. We'll pretend this clicker is my cell phone, right? Like suddenly, we started picking up these things and having them in front of our faces all the time, and they are not tethered to power supplies. We needed batteries that could last all day long. And therefore, the place where we started seeing innovation in architecture was in the mobile phone industry, first with ARM32 processors. And then people realized, wait a second. If saving power is useful for keeping people's cell phones lit so that they can go and click on TikTok all day, what if we could use it in the data center too? And that's where ARM64 and RISC-V and kind of all these architectures that we've now seen springing up have come from, because they've taken this innovation of suddenly caring about power and realizing this has an environmental cost and this has a cost that can be passed on to the cloud computing consumer. So even with that, that wasn't enough to change the game. What really changed the game was the fact that Linux won in the data center, that open source software won in the data center, that we no longer were kind of tied to this idea of you get this packaged piece of software from your vendor, and either it works on the architecture or it doesn't work, and you cannot use that architecture. But having open source available where you could just recompile your own dependency tree and make it work on a new architecture, that's what enabled people to start using this at scale, including Honeycomb. Another piece that I think is also covered by Matt's talk a little bit is complex versus simple instruction sets. The fundamental reason why ARM is the future of computing and why we should think about adopting workloads, serverful and serverless, is that ARM does not bring the legacy baggage of 40 years of x86 32 along with it. There is a ton of the surface area of every Intel and AMD die that is devoted just to translating x86 assembly into the underlying simple instruction set that is used under the hood by the Intel and AMD chips. But if you could just get rid of all of the decode units because it all just translates directly to what the chip is doing, that's a lot more power efficient. And you've been told a lie in terms of, oh, like that has 2 vCPU. That means that I can run 2 things in parallel at all times, right? You can decode 2 things in parallel. You cannot execute 2 things in parallel with x86. Whereas with ARM, 1 virtual CPU is 1 core, decode and execution. And that means that you are not contenting yourself. Sure, it might have worked in the server environment. It might have worked on the desktop and on your gaming PC where you are not contenting yourself, where 2 different workloads are trying to do different things and they are spiking the CPU at different times. But when you are running an at-scale cloud workload, if you spin up, like Honeycomb spins up, hundreds, 100,000 invokes, right? And each of those is using four cores. Those 4 cores are all going to be demanding the exact same profile of things that they're trying to get the CPU to do at the same time, and they're contending the resources. So we see less tail latency and less performance variability. So these processors are really almost, you can think of them as being built for the cloud first, because they are designed to be resilient against everything from shared cache attacks, Meltdown and Spectre. They're designed to be resistant to contention of you against your own workload. And they're also better for the environment because they just consume less power, because the more surface area and the more transistors on the die, the more power it consumes. So Honeycomb adopted Graviton pretty early on in the year 2020. And we found that they delivered significantly better tail latency, and also that Amazon was willing to offer them to us for 10% less per core. And this was initially a little bit of a process, right? We were trying to figure out which workload to migrate, the serverless workload, the serverful workload. How do we actually make sure that, how do we spin up a brand new kind of base stack from scratch? And the answer is that your base operating system is a Docker layer or is an EC2 image, and you can basically go and take your infrastructure as code rules and apply them to generate new images based off of whichever architecture is appropriate to the task. And then it's a matter of, does your code compile? Does it work, and can you produce a good build artifact? So one of the things that worked in our favor here is we are a Golang shop. And I know this sounds weird because I know that Rust and C++ are kind of, if you are working close to the bare metal, you have to use it in order to get the best results. But in our experience, we use Go for readability first. And for anything that's really, really performance critical, that's where you have the ability to drop from Go into assembly language in line with the Go compiler. So we were able to at least very quickly, quick and dirty, cross-compile. Does it work? Does the binary work? Do our tests pass? That didn't necessarily surface whether it was going to be performant, but we wanted to just validate it and see what happened. So you just set an environment variable, and Go will pick it up and Go will cross-compile. And by the way, this was before the M1 Max started shipping. But ever since M1 Max started shipping, suddenly everyone and their dog has had to care about making sure their stuff compiles for ARM anyways. So it was initially a little bit painful for us. But I think for you all, this journey to using ARM software is a lot easier because of the fact that everything that you might possibly use has already been tested. You may already be using an ARM laptop sitting here in the audience right now. But if you're using C++ with hand assembly, maybe that's not the first workload to migrate. Focus on things that are either things that have runtimes like Java or Python, or things like Go where you can easily cross-compile out of the box. So it builds without errors. Now what? Well, how do we verify that it's actually, is faster, that it's cheaper, that it saves the environment, right? If it's 10% faster if it's 10% cheaper per CPU second, but it takes twice as long to run, you haven't actually saved any money. You haven't actually saved the planet. So we started running A/B tests. And the interesting thing that we discovered very quickly is that the ARM processors actually seemed as if they were slightly slower. It seemed as if we were going to need more of them. So we were saying, hey, we're going to auto-scale everything to keep everything at 50% CPU utilization. And we did that, and it was like, hey, by the way, you're going to need 30% more of these to maintain 50% CPU utilization. So it turns out the error there is that thing about multi-threading that I mentioned. Do you know why we had to run at 50% utilization? 2 decode units, 1 execute unit. So it turns out that with ARM processors, we were able to set our auto-scaling targets much, much higher and still maintain the same target latency. We were still getting the same performance with the higher CPU auto-scaling threshold. So we were actually able to cut the number of instances that we were running by 20%, have each instance be 10% cheaper, and actually get that headline number that AWS said of this is going to be 30% more price performance than the Intel previous generation instances. Cool. So we migrated our ingest service, and then we migrated our storage workers, the ones that are kind of doing that translation of the incoming data into the columnar storage format, and then reading it on demand, at least the local SSD part. So we did that, and we found basically immediately that the P99 dropped. That when someone ran a query that hit only local storage, that it went from taking, I think, 2 seconds at P99 to 1 second at P99 if it was a pure local query, which I think is really cool, right? Like, because we're in a situation where we stopped contending with ourselves. And that enabled us to grow and grow and grow without having to scale out our number of instances, which is pretty cool, right? And then we did that trick again, because Amazon released a new generation of instances, so we tried it out, and sure enough, further drops in the median latency that it takes to run a local query and a P99 latency. So that's kind of what we saw. And we also saw better CPU utilization, again, which means that we can crank up the screws even tighter. And there's a new generation that's out, and it's unfortunately not available for Lambda yet. So Lambda, funnily enough, is still stuck in Graviton 2, which was released in 2021. But the good news is that when you're comparing Lambda versus Lambda, Lambda x86 versus Lambda ARM, you're comparing essentially 5th generation or 6th generation instances against each other, because it's not like Lambda x86 gets the newest and best gets the newest and best instances that Amazon has released either. So, it's essentially right. Like, Lambda is a value product, right? It's a scale-out product. It's meant to be available to absorb massive spikes, but it does not offer the best single-core performance, whether you're running on ARM or x86. But generation to generation, right? Like, in the case of server full applications, we were able to see, after doing the switch to ARM architecture once, we were able to see our performance basically double per core within 3 to 4 years, which I think is really cool. So we have been 100% ARM servers for 2.5 years. And we turned off our last x86 server in April of 2022. And also, with regard to ARM, we've started switching our Lambdas over. But the process of switching our Lambdas over actually was really fraught. We thought, sure, the server full workload worked so well when we switched it. Why can't we just push this magic button that says make go faster? And why doesn't it magically work? So I'll call out the numbers on the bottom of this. You'll see that with the same sized AMD versus ARM architecture Lambdas, it was 50 to 100% worse performance with ARM initially when we had just naively migrated everything over. So I had to revert that experiment very quickly, because obviously we're not going to do a thing that was inefficient, slowing our customers' experience down. So we flip the feature flag, back off. So only 1% of queries were running against against ARM. And we started figuring out and scratching our heads and working with our AWS team to figure out, like, what in the heck is going on? We saw such great results with serverful. Why is serverless so slow? So it turns out it was 3 or 4 different things. First of all, it turns out Amazon has a ton of old x86 instances sitting around that they can give you for Lambda. If you are like us and you rock up and you say, 100,000 invokes, please, and it's for a brand new architecture they haven't fully rolled out, you're going to experience a little bit of a capacity crunch. I can assure you, by the way, that problem is no longer there. There's a lot of Graviton 2 floating around because Graviton 3 and Graviton 4 have come out. So now there's a lot more capacity available, but we didn't know that at the time. Again, this is why talking to your account team is so important. Secondly, at the time, Go 117 had introduced for x86 the ability to call between functions without hitting the stack, without passing every argument to the stack, to memory, and then getting it back. But it didn't implement that optimization for ARM until Go 118. So we had to wait for that to happen. And then third, we discovered that unlike the rest of our workload, where everything just ran even without hand assembly optimization. The LZ4 library, because we, of course, compress our files before we send them off to S3, the LZ4 library had been hand assembly optimized for x86, but the version of it that we were using for Go had not hand optimized the ARM64 library. And it turns out that was part of that core critical loop, right? Because part of analyzing people's data involves decompressing it once you get it back from S3. So we contributed upstream a fix that allowed the LZ4 library to be hand assembly optimized. And suddenly, between all three of those things, suddenly we started getting that 20% better price performance. And also, one side note, it turns out that if your Lambdas are cold starting, or even warm starting, and they don't have an open connection to S3, you wind up paying the price to open a socket, to do an SSL handshake, to validate that the S3 SSL certificate hasn't changed since you built it. And yeah, that's something that you can just skip if you trust that Lambda to S3 communications are secure. So we were able to flip it on, and it took us basically from November 2021 until October 2022 to get enough capacity into place for us to become 100% Lambda, or at least 99% Lambda. And we were actually able to see that this is a misleading graph, actually, because it looks like the latency is equivalent or about the same between x86 and Lambda. The thing I haven't told you is we were able to take 20% of the cores away from the ARM Lambdas. So each CPU second that, or sorry, each millisecond that Lambda is invoking on ARM64 is costing 10% less because the cost per core millisecond is less on ARM. And also, we are provisioning fewer cores because it was still able to keep up even when we took the cores away. The magic of power-efficient CPUs. And actually, earlier this week, I actually submitted a pull request that just deleted all of the x86 Lambdas. After running continuous validation of, hey, we're going to hold back 1% of our traffic just in case we need to swap back. Hey, we're going to hold back 1% of our traffic. The day never came when we had to switch back from ARM to x86. So we're like, OK, technical complexity, like every migration has to have an endpoint. This is the end of the road for our migration. Like we're killing off everything in our infrastructure that is not ARM, whether it's serverful or serverless. So should you do this at home? Maybe. I think the question is basically, in the case of serverful versus serverless, do you have a workload that you can map reduce? You don't have to, embrace the, oh, we're going to go API gateway first. We're going to decompose everything into serverless functions, right? Like you do not have to go on that journey. You just have to find a workload that is embarrassingly parallel that you can invoke. So, I think it's really cool when you have a greenfield opportunity like Nubank did to kind of basically make everything serverless or containers. But in our case, we started with a very server-full workload, and we're able to still find value out of serverless. Just be mindful, right? Like, as I was saying, someone calls Honeycomb via the API and doesn't need the results within 10 seconds. Like, maybe don't run that against Lambda. That's just going to run up a very expensive bill and not actually give the user any better behavior than if it took 5 minutes to do. We still have our local serverful workers pull individual files off of S3 if they're being asked to pull less than a few thousand files. Like it just makes sense to process those in serial on a small number of CPUs because there is a cost to invoking a Lambda. There is a cost to spinning up that worker. Make sure you do capacity planning because, yes, serverless is serverless, but serverless ultimately runs on physical servers. So make sure that your cloud provider has enough capacity available, similar to how you would check, does your cloud provider have enough spot capacity available? Does your cloud provider have enough Fargate available, right? Like, make sure that you're communicating about how much you intend to use. And actually, do performance testing. I loved the opening keynote remark about, like, are you doing a regression tests, right? Like, do you know for sure what your performance thresholds are, and can you validate continuously that your binaries can continue to meet that goal? And make sure everything is tuned and optimized, and use observability to actually make sure that you are experimenting, right? Like you're not just introducing chaos, but they are actually validating, does this make sense for us? Maybe it does make sense for you, maybe it doesn't, but you're not going to know unless you're actually measuring the before and after. So when you do this, as part of an ARM migration, this means that you're going to be able to make your cloud bill go down and save the environment by consuming less power. But you kind of have to be prepared to do that homework. You have to be prepared just in case it doesn't go 100% to plan. But there are some easy things that you can do today. For instance, if you're using a managed service like RDS, if you're using a managed service like OpenSearch, you can just click the box that says, yes, please use Graviton for this. And of course, validate that your CPU utilization goes down, validate you can run more workload, but that's an easy way that doesn't involve having to cross-compile or change your code or set up multi-arc Kubernetes. At the end of the day, nothing matters unless developers are happy. If you are running a platform, right, like your users are your developers. If you're developing software as a product engineer, right, like your users are the people out in the field. But either way, right, like we need to try to get them the best possible results with the least possible cost and with the least possible environmental impact. So that's Flurry Fong-Jones. It's my dog. This is our book, Observability Engineering, in case you're interested in learning more about how we put together this data store, including the Lambda pieces. And overall, more than 2x price performance from 5th gen to 8th gen. And we've had basically our service has increased in scale by 20 times, and our cloud bill has not gone up by 20 times, I can tell you that. So go forth armed with this info, pardon the pun, and thank you very much.